Risk is a measure of the probability and severity of undesirable consequences. For dam and levee safety risk assessments, these undesirable consequences can be associated with life safety, economics, or non-monetary consequences like environmental destruction. Of these different sets of consequences, life safety is paramount and the primary factor that guides our decision-making process for dams and levees. In a risk assessment, we assess the probability of failure, which will be a function of the hazard, hydrologic, or earthquake, and the structure's performance. Then we consider the consequences of failure, which will be a function of who or what is downstream at the time of breach inundation, and the amount of inundation that results. For our purposes, the Federal Emergency Management Agency's definition for dam and levee failure is used. Failure is characterized by the sudden, rapid, and uncontrolled release of impounded water. To reiterate, dam and levee safety risk will be a function of the hazard and its likelihood, the estimated performance of the structure given the hazard, and the expected consequences. The consequences will be a function of who or what are in harm's way, how susceptible to harm they are, and how much harm is ultimately caused. This figure illustrates the three components that make up the risk equation: hazard, performance, and consequences. In dam and levee safety, there are three different types of risk we will consider: incremental risk, non-breach risk, and residual risk. Incremental risk is the same as the infrastructure risk and can be the result of breach prior to overtopping, a component malfunction, misoperation, or overtopping with breach. This is the risk associated with the dam or levee and its components not performing as intended. Even when a dam or levee performs as intended, there is still some risk of inundation. This is referred to as the non-breach risk. For dams, this is typically associated with releases through the spillway, whereas for levees, it is typically associated with overtopping without breach, but we also consider overtopping without breach for dams as well. The sum of the incremental risk and the non-breach risk is our third type, residual risk. Residual risk is also known as the flood risk and refers to the total risk of inundation within the floodplain, and for dams includes the reservoir area. While we calculate and discuss all three with decision makers, the Dam Safety Action Classification or DSAC and the Levee Safety Action Classification or LSAC, which are used to prioritize the inventory, are informed only by the incremental risk, the risk associated with the structure. Risk is the product of an event's probability and its consequences. As discussed earlier, incremental risk is used to prioritize the Corps' dam and levee inventory and is the risk associated with the dam or levee and its components not performing as intended. The incremental risk is equal to the product of the total probability of failure and the associated consequences. The probability of failure is equal to the product of the hazard probability, hydrologic or seismic, and the conditional probability of failure, which is known as the system response. In dam and levee risk assessments, system response probabilities are estimated for each credible potential failure mode. The risk of each individual potential failure mode is calculated and combined to calculate the total risk of the project. Probability is a measure of the degree of belief in what we are predicting based on the information or evidence that we have. What we are predicting are uncertain events that occur in the future. Probability can also be an estimate of the likelihood of the magnitude of an uncertain quantity in addition to the likelihood of the occurrence of an uncertain event. One of the rules that we discuss here, and we'll discuss again when we get into event trees, is that a probability must have a value between 0 and 1, no less, no more. If something has a probability of 0, it cannot happen and is impossible. And if something has a probability of 1, it is certain to occur. Probabilities can be marginal, joint, or conditional. A marginal probability is the probability of a single event occurring irrespective of other events. It is independent of other events. Said another way, it is not conditioned on the occurrence of another event. Joint probability is the probability of one or more events occurring at the same time. Conditional probability is the probability of one event occurring with some relationship to one or more other events. Conditional probabilities are something that we deal with quite often when working with event trees and the pathways through those trees. The nomenclature for conditional events is a vertical line, which is sometimes called a pipe, that separates the variable and can be read as either given that or conditional on. So the term in the third bullet would be read as the probability of B given that A occurs, because B is conditional on A. If A and B have a conditional relationship, then observing that A occurs gives you additional information about the probability that B also occurred, and vice versa. Consider a simple example. We have two standard six-sided die. If we were to roll die A, the probability of rolling a 4, event A, is 1 in 6, or 16.7%. The probability of rolling a 2 with die B, event B, is also 1 in 6, or 16.7%. These are both marginal probabilities. Now let's say we want the probability of rolling a 4 with die A and a 2 with die B, or in other words, event A and event B occurring at the same time. This is a joint probability and can be calculated by multiplying the event's marginal probabilities together. The probability of rolling a 4 with die A is 16.7%, and the probability of rolling a 2 with die B is 16.7%. So we multiply those probabilities together to get the probability of rolling a 4 with die A and a 2 with die B on the same turn, which gives us 2.8%. Next, let's consider a new event, event C, where the sum of the values of die A and die B is greater than 7. Also, let's say we have already rolled die A and it was a 4. Knowing that event A has occurred and that the roll was a 4 tells us something about event C, doesn't it? We now know that there are only 3 outcomes from the roll of die B that can be added to the 4 of die A to get a value greater than 7. Therefore, given that event A has occurred, the probability of event C is 50%. This is a conditional probability. There are two main interpretations of probability: subjective probability and statistical probability. Subjective probability is what we most often consider during a risk analysis and is a quantified measure of belief or judgment in the likelihood of the outcome we are evaluating. We do this by considering all available information we have, hopefully with a minimum level of bias. Subjective probability is affected by the state of understanding of a process, the judgment regarding an evaluation, and the quality and quantity of information, all of which can change over time as the state of our knowledge changes. This change in knowledge could be the result of subsurface investigations and drilling, or material testing. It could also be the result of performance observations. Perhaps an embankment is loaded by a stage it has never experienced before, and seepage is observed. Or perhaps seepage becomes turbid, or its volume increases. These observations can obviously change the probability we might estimate for a given event. Statistical probabilities can be thought of as the outcome of a repetitive experiment. Such statistical probabilities are covered in the Best Practices Training course and are used heavily by the Bureau of Reclamation in their risk assessments. They have statistics for their inventory on the rates of observed initiation, and they adjust those rates up or down based on factors specific to the dam being evaluated, and from there they arrive at a probability estimate. ICOLD, the International Commission on Large Dams, has statistics on dams worldwide which can be helpful. The Corps of Engineers considers statistical probabilities during risk assessments, but leans more heavily on subjective probability. Over the last several years, the Corps has been collecting and compiling data on dams and levee incidents, which will eventually be used to calculate a rate of occurrence for different mechanisms. This data, when it is ready, can be considered during a risk assessment. Random variables are used to represent an uncertain quantity whose value can take on multiple possible outcomes. It depends on some probability distribution rather than a deterministic rule. This uncertainty can be the result of natural variability or lack of knowledge. Despite its name, random variables do not necessarily have to describe a random process, which is usually indexed by time, but they can. Let's say you put $1,000 in a bank account with interest compounded annually. The interest rate is a random variable that would be determined the moment you put the money in the bank, and it does not change after that. How the amount of money in the bank account changes is a random process that is dependent on the interest rate and the time. Uncertainty is the lack of sureness or confidence in our predictions or conclusions due to imperfect knowledge concerning the present or future state of a system, event, or situation under consideration. Uncertainty with respect to natural phenomena is defined as aleatory uncertainty or natural variability, while uncertainty associated with a belief is defined as epistemic or knowledge uncertainty. The degree of uncertainty often depends on the information available at the time and can range from nearly complete sureness to an almost complete lack of conviction about an outcome. Knowledge uncertainty and natural variability were mentioned on the previous slide. Here are the definitions for both terms. Knowledge uncertainty is a result of imperfect knowledge concerning the present or future state of a system under consideration. It leads to a lack of confidence in our predictions, but this type of uncertainty can be reduced by collecting more data or better information. During a risk assessment, teams are to identify sources of knowledge uncertainty as it relates to potential failure modes, and they should show how sensitive the risk estimate is to these uncertainties. Based on this information, recommendations can then be made to reduce uncertainty should the uncertainty have a large impact on the estimate and the ultimate decision. Natural variability is an inherent property of the system or population that is being evaluated. This is something that can be better characterized and addressed quantitatively with more data, but it can never be reduced or eliminated. Module 4 of this course will discuss uncertainty in more detail.